Hello, everyone, and welcome to a Power Engineers webinar. Thank you for joining us for our first installment of Power Engineers Grid Modernization webinar series. Today, we're going to discuss preparing your GIS data for use in advanced utility applications, and in particular, 3 proven methods to prepare substation data for the future. Before we start, just a quick reminder that all attendees of this webinar will be in listen-only mode. But if you have questions as we're going through, we encourage you to submit those questions using the Q&A box in the lower right-hand corner of your screen. And please submit your questions to all panelists. We'd love to hear from you. We've scheduled time to answer your questions at the end of the webinar. And finally, this webinar is being recorded, and we'll provide you with a link to the recording in case you'd like to share it with others on your team who couldn't attend today. Let me briefly introduce myself. My name is Jana Constant, and I'll be moderating today's webinar. I am a Senior PM and Strategic Consultant for Power's Geospatial and Asset Management Business Unit, and I've been working in the GIS and utility industry for 30 years. We have a great lineup of knowledgeable presenters today. Larry Wilkie and Terry Kendall will be providing you with the majority of the webinar content, and I hope you find the information beneficial. Many of you know Larry. Larry is a strategic consultant with over 30 years in the industry. Prior to joining Power, he worked at Burbank Water and Power for 20 years. Larry has been leading the charge with many ADMS solutions, including substation modeling, to support grid modernization. Terry Kendall is an area lead and integration expert in our business unit with over 37 years in the industry. Terry is also managing a team of consultants here at Power that is focused on the machine learning aspect of substation conversion to support ADMS. And our special guests today are Remy Myers and Ray Hani. Remy most likely doesn't need an introduction. Remy is the Esri product manager for the ArcGIS utility network. He has over 20 years experience using GIS for land management, transportation, public health and utilities, and is a graduate of the University of Georgia with a master's degree in geography. We really appreciate all the support that Esri provides to their partners, and Remy is a big part of that great partnership. Our second special guest is Ray Hani, who is joining us from Chelan PUD, where he has 30 years of asset management systems, GIS, and Maximo experience. Ray is also renowned for fly fishing throughout the central region of Washington. Power appreciates your partnership with Chelan in providing support on their GIS, OMS, ADMS, and substation design. Thanks for being here today, Remy and Ray. Before we get to Remy's opening comments, I want to give you a brief overview of Power Engineers for those of you who don't know us. Power got started way back in 1976 by 2 electrical engineers and their dogs in Pocatello, Idaho, and since then, we've grown to over 2,800 employees in 50 offices throughout the US and Canada. The company is divided into several divisions that are shown on the right side of the slide. Power Delivery is by far our largest division, and they cover a full spectrum of engineering services, including ADMS and grid modernization, which are being covered on this webinar. Our Geospatial and Asset Management division, which Larry, Terry, and I represent, covers all aspects of GIS and asset management projects, from initial planning all the way through deployment, training, and ongoing support. And we've got a very senior team that averages over 20 years of experience. We work very closely with Power Delivery on many types of products. Power has been an Esri business partner for over 20 years, and we're an Esri Gold partner. We were in the first group of companies to achieve the utility network specialty, and we received an award from Esri for being the first to help an electric utility get fully into production with the utility network. Once again, thanks for joining us today. I really hope that you enjoy this webinar. With that, let's get it kicked off with Remy Myers from Esri. Remy, over to you.
Thank you so much, Jana. It's really exciting to see all the products and projects that are coming out from Power Engineers. No doubt, it's really always an honor to be able to co-present with you guys. I've been working with Power Engineers as a customer since the early 2000s, and I was really appreciative of all the work that you've done in helping us at Southern Company build network models and really interesting GIS solutions. But one of the things I always appreciate, and I think you'll see it here today, is Power Engineers is focused on engineering. Might be strong GIS, but it's strong GIS for engineers. I think you'll be really interested to see some array solutions and some of the great work that they're doing down in Chelan. So let's talk about the emerging transition of GIS for utilities. As you probably know, core drivers of a utility are always going to be safety. Safety comes first. Reliability, customer service, grid modernization, asset management, and innovation. And all those things are integrated, and Esri is here to provide solutions for all those drivers of a utility using the ArcGIS Enterprise. Now, this enterprise gives you the ability to take all these drivers and utilize focus maps and apps to provide solutions that are customized and detailed for your user base. And one of the things that really excites me is how our user base is growing. Used to be these GIS departments were small and tightly integrated. Now they're much larger with a much larger user base. So I love this graphic, but it really doesn't tell the story because all these maps and apps are all system integrated. They all work together almost like a constellation of solutions. And these solutions all have integrators and ties, things that bind them together. And it really gives you the ability to extend your GIS throughout the entire enterprise. Now, today's topic is very interesting to me because, substations can be some of the most hazardous, complex, and critical elements of the electric grid. And the role of GIS support for those substations has changed drastically in the last 10 years because of the implementation of SCADA and AMI. And it's truly put a strain on our ability to manage those big data systems. Yeah, that's really why you've had an OMS and a DMS transition to an ADMS, and Larry will talk about that shortly. But our ability to communicate and collaborate across these big data sets are going to be critical to support your infrastructure. So go ahead, Larry, take it away and show us what you got.
Thank you, Remy. So today I'm going to go through 3 examples of substation modeling, kind of an approach that goes from more traditional to more advanced, let's say. But before I get started, I want to familiarize you with some acronyms that might slip out during my explanation of these substation digitizing methods. So first off, we've got Advanced Distribution Management System. That is just like adding advanced applications to a traditional DMS, which is a distribution management system, which generally has from the substation transformer downstream through your feeders and has that distribution SCADA. On the other end, we have EMS, which generally is the transmission systems, energy management system. Then you might hear me say DMD, or dynamic mimic display. That's the display that the operators use, similarly to a GIS, but it's more integrated with their SCADA. And then GN, Esri's geometric network. PSPS, that's a new one for us. That's the public safety power shutoff. And that's being used in the western states right now for fire mitigation. So in heavy wind events or something, they'll shut down the power just so that none of these lines maybe make a spark and create a fire. Utility network, I did not show you a abbreviation for that because that's the Esri's new extension in the Pro environment, and I'll try to stay away from abbreviations in that. Today, there are more points to monitor for electric system operators. Back in the day, the operators would just buy or generate enough power to meet the aggregate of the current flowing through each of these feeders. Today, the standard usage curves may be the same, but they don't look the same due to things like distributed energy, such as solar or microgrids, and battery storage, just to name a few. So on a side note, I was watching the World Series last night, and I saw this new Hummer truck ad, and they said that in 10-minute charge, it'll get them 100 miles. Can you imagine what that 10-minute charge is going to do to our grid? So that's going to probably be a lot of current flowing to get those batteries all charged up. It just was interesting to me. So the substation model needs to be accurate, monitored with SCADA to appropriately mitigate things like reverse load flows, demand response, and peak shaving. So that's kind of the things that drive this business. Another driver is engineering planning. So engineering planning needs information from the substation power sources and transformers to properly calculate load flows and tune the model for current and future load allocations. So it makes a difference when maybe two substation transformers, like we see in this picture, are in the same substation. So they could be utilized to share that load for all the feeders. They could be used to be in parallel for that load, or they could be used as like a master and spare scenario. Every one of these scenarios puts a different usage onto that feeder level and into all of our controls for operating. So GIS has traditionally started from the substation circuit breaker in order to provide a clean feeder level trace with no looping from substation bus bar. So without a subnetwork controller in the substation bus bar, subnetwork controllers we'll get into later, which are in the utility network. Without that network controller, all the feeders would just connect all together. So today we have methods to incorporate GIS into the complete electric model. So I'm going to tell you why PG&E decided to do a direct draw within their ADMS's dynamic mimic display in order to converge the substation information into the model. Then I'm also going to tell you how Portland General created a separate feature data set to isolate responsibility and security between the substation and the distribution GIS editors. And then finally, Ray Hani will tell you a little bit about his confidence in power and why Chelan County decided to utilize the tiered structure of Esri's utility network to create topology entirely within a single connected GIS model. PG&E's requirements. The infamous public safety power shutoff. It's now the standards by which California utilities are operating. It's spreading to Oregon, Washington, Idaho, and Arizona. So this was the main driver for PG&E to select an ADMS, and it had to have the capabilities to isolate or sectionalize feeders or areas based upon like a wind event, maybe tied with some dryness and vegetation conditions of a service area. So once they shut that down, after a patrol and all clear, the operators would re-energize. And we all know what happens when you re-energize. You get an end rush current on the system, and it needs to be managed at that substation protection level. So PG&E operators, they weren't ready for true geographical representation or orientation. So they wanted the high side of the substation at true north, always, no matter what it looked like geographically. And then they wanted the feeder getaways all at the south or bottom of the display. So this became even trickier when a substation had different sections oriented in different geographical directions. So the example that I'm showing here has this one section in the upper left of the GIS kind of facing east and west. And then this lower section in reality facing north and south. For PG&E, we had to rotate those and draw those. And this is what was the reason why we drew those directly in that dynamic mimic display. So because PG&E had a fast track to implement this ADMS and manage these PSPS incidents, it exposed a myriad of duplicate data, and it couldn't all be consolidated before the go-live requirements of the ADMS. So a phased approach will be used later to determine the single source of truth and proper integrations for things like substation GIS, substation single line drawings. Those are the AutoCAD drawings that are used by the substation design and engineering group. Aspen single line topology, that's some single lines that are used by protection engineers. They actually draw those in there so that they can figure out what the protection schemes are going to be. And then SIME topology, that's used by planners. Every one of these had its own topology. So they're drawing in 4 different systems right now, and a 5th going to be the ADMS. So eventually we're going to consolidate this probably in the UN and be able to extract from the UN to support all of these different systems. So this disparate data and Power's knowledge of these systems allowed us to generate scripts to compare this data and reconcile issues found prior to the ADMS imports. So another method that was used was Portland General's separate feature data set. So they had a separate feature data set, both of them within the geometric network, and they were at an ESRI 10.6.1 model. So Portland needed traceability for their OSI ADMS. And in this project, although it was a geometric network digitizing project, we used ArcGIS Pro because you can apply grid lines at a proper angle. You can rotate those grid lines so that we could supply equal spacing between devices, even when the substations were not oriented in true north. So this rotation of this grid in Pro allowed us to place those things in very neatly. So some of this spacing is totally required for getting in like SCADA elements and stuff like that between buswork. Other requirements were the security. So we could put the substations in the same database, but we created its own feature data set to isolate the roles for distribution editors to be separated from the substation editors. Then we created these stitching points, and those stitching points were going to allow us to traverse between the substation geometric network and the distribution geometric network. That'll help us to supply that total network for the ADMS. So an example of these stitching points, we have this substation feature data set, and we're showing you here the 2 transformers with some maybe circuit breakers that tie the bus together. And then circuit breakers that are traditional for the GIS would be items like 13144, 13141, 13148, those types of things. Then on downstream, it goes through a couple other features and then to those stars. And those stars are what's representing the stitching point. Then in the distribution feature data set, you have your traditional substation circuit breakers. And then you see where the stars are to stitch the distribution feature data set together. And then downstream from there, we have all of our feeder information all the way to the customer meters. So in our third example, I'm going to introduce Ray Hani, and he's from Chelan County Public Utility District. And he's going to tell us more about how they're implementing using 3 tiers of the utility network model and some sub-network controllers that let them contain the high voltage transmission through the substation transformers and onto the medium voltage distribution to supply the network for OSI Spectra DMS, all in one network.
Yeah, hello everybody. This is Ray Hani. I'm the Asset Management Systems Manager at Chelan PUD. I've been in the business for over 30 years, and Chelan County PUD is a small electric utility in central Washington. Even though we have a lot of generation on the Columbia River, we have a fairly small distribution system. And we've been an Esri shop for about 25 years now. And we have started our UN migration here now with Power Engineers' help. The main driver for us is we also had a directive to implement OSI's Spectra ADMS system. So that required up in the ante for GIS, basically. For instance, we never had to model substations at all in our current GN model. So over the last 6 months, we've been changing that and updating all of the substation internals in our GIS system. We also wanted to test a UN migration and get ready for the eventual migration to the UN, but like I said, the OSI project sped that up. We have a really tight timeline that you can see on this chart here. So we had to bring in a lot of Power Engineers' help too to meet that timeline. One thing we really considered is we didn't want to integrate to ADMS twice, knowing the UN was coming along here pretty quickly. So even though in production we still edit against the GN, Power Engineers has already helped us set up a UN model that's going to be synced, nightly or weekly, so we can use that as the single integration point to OSI. Yeah, like I said, the UN roadmap was built around the OSI implementation. We also had a secondary requirement to improve our Millsop windmill integration. So that's also a driver for going to the UN. And one thing I can say, over the last 6 months, we've actually been improving the GN data to be ready for the UN migration. It didn't turn out to be that big of a job for the substations. We had one GIS editor working on remodeling our 50 substations, and it only took them about 100 hours. He's a real experienced editor, so it helped to have somebody with that knowledge. Even though, granted, this was just the topology that's modeled in our substation drawings for now. There'll be later refinements when we need more attributes for the ADMS system. And onto this slide, actually, you'll see all the network topology resides in our GIS now. We still have the GN and we have the synced UN environment kind of working together. And you can see, in the UN, it's all one network with sub-network controllers between the different voltages. Now, Power came in and helped us with this by doing an initial assessment of our data and of our GN model. So they really helped out by giving us a plan for what it would take to improve our data, improve our model to fit in the UN. And then they actually have already developed the data migration routines to copy our GN data to the UN. And the good news is that just got installed this week. Just this week, we have the fifth release of the GN to UN migration, and it's getting installed on our network this week to actually start syncing up regularly. So we're making pretty good progress. Power actually helped lead a team too to clean up our GN data. Part of their assessment was telling us what data in the GN would have to be cleaned up first before it could be migrated. That didn't turn out to be too bad for us. Somebody, you could call me later if you wanted to, or if you want to know what the costs of that were. Then in this three-tier structure, MillSoft and OSI will just use a transformer to meter relationship. Like we aren't going to model our low voltage secondary too closely. GIS will just maintain basic information about that. Then onto this slide, actually, as part of this improvement of our data and moving to the UN, we've set up an equipment data catalog in our GIS because we realized both MillSoft and the ADMS were going to need better equipment data to support all the advanced grid functionality. So we've just recently set up catalog tables in the GIS database. And what they do is follow this SEQ file format, which is a multi-speak format, because fortunately both MillSoft and OSI can import data in this SEQ file format. So to accomplish that, it was pretty easy, really. We just imported the SEQ file format that we had in MillSoft today and then improved the data accuracy, went through and made sure that data matched our GIS information and our information in Maximo closer. And now what we can do is just regularly extract the data from the database in that same format because the tables in our GIS database are already structured to match that multi-speak format. So even though the tables reside in GIS, asset information will be extracted and integrated through Maximo also, some of the more complex like nameplate data and maybe setting changes. Then eventually our wire specifications will get integrated through Maximo too, because wire are inventory items in Maximo. Yeah, and the reasons we're using the catalogs directly in the GIS tables is so that the timing of the data going to ADMS can be more in sync. We didn't want to create a disparate database somewhere outside of GIS and then start running into problems where the two sources were out of sync. All right, with that, I'll be available for questions toward the end. And I'm going to pass on the presentation over to Terry.
Thank you, Ray. Machine learning is a technology that Power is looking at for a variety of power delivery and geospatial asset management applications. We think it's one of those transformational technologies for the utility industry. Our innovation teams are looking at different ways that machine learning can help in modernizing the grid, how it can be used to create and maintain the grid's digital twin for these advanced grid applications. When paper is all you have, manual conversion of substation drawings is really what's required to get those into GIS. With machine learning, it is possible to teach a machine how to read the substation drawings and programmatically create the features in GIS. As you can imagine, 100% conversion even for the geometric network is a challenge, and the utility network an even greater challenge. But first, what is machine learning? Let me give you a definition. Machine learning is a technology, an application that can automatically learn. It's an application in the artificial intelligence world that can automatically learn and improve without being explicitly programmed. Machine learning then again focuses on accessing the data and learning for themselves. The machine has two primary ways of learning. There's supervised learning, where samples are presented to the machine. The machine learns how to recognize those features that you've presented to it. There's unsupervised learning, where all you have is the output, and it needs to learn what that input is. You may start with supervised and let the machine kind of improve on itself. For capturing substation drawing features, we had to teach the machine how to read those substation drawings. So we taught the machine, or we trained the machine to detect substation features in a substation drawing image, so a PDF to a JPEG or some sort of raster image, so that the corresponding features can be created in GIS. The machine is trained manually by manually labeling the features in our use case 100 sample substation images. The machine then learns from those sample images. Once the machine has been taught to a level of acceptable data loss, the machine can then process all the other images and label those images with the features it has been trained to recognize. After the machine has detected all the features in the image, post-processing occurs to read the features that the machine detected and then put them directly into GIS. Following that, you have to do some post-processing. So we read the machine detecting features from images, we apply some metadata for spatial referencing, and we create those features relative to an origin in the image, whether that's next to a point in your existing GIS or it's some metadata that we have provided. Then we do some post-process the image to remove all the noise like borders and title blocks, and then ignoring the detected features, we're left with the line work that represents the bus bars and maybe some conductor in the substations. These lines are then converted also into GIS features. So the overall process looks something like this. First, the machine is trained with the sample substation images. The labeled features in the sample images are then used by the machine learning algorithms to determine the best machine model with the least amount of data loss. So depending on the quality of the labels and the data loss that you're receiving, a couple of iterations might be required to further train to an acceptable level of data loss. Once the machine model is built, the next step is to run that machine model against the remaining substation images to detect and label the features that the model has been trained to detect. The labeled images are then used by this post-processing that has processes that read the images, extracts the detected features, and creates the GIS features. And then just highlighting the post-process on this next slide, really you detect the features, and then first machine is trained with the sample images, and then those are the rest of the images are run through and they are detected. Then the geoprocessing tools are used to determine the noise, what the title blocks are, the annotation clouds, extra line work that might be in there, some things that we've told it to not include, and essentially remove that noise. And then the results, if you kind of subtract the detected features from the noise, is the line work that's left, and then we can convert those into GIS features. So depending on the conversion requirements, we think we can really lower the cost of converting paper maps. Of course, this is all depending on the requirements. The savings could be significant, but it can vary widely. For many clients, just getting the substation features in with the geometric network would be a huge achievement and leave them better prepared for the utility network down the road. For others, where significant post-processing for space management, entering additional data, establishing the utility network, the savings would vary widely depending on where you're at and what the specific requirements are. Finally, this is just one way we are using machine learning. Power has several other projects, and we see lots of opportunities using machine learning in the geospatial asset management business, including compliance reporting, inspections, whether drone photography or ground-based photography, being able to automatically determine anomalies just for asset management, asset inventory, and vegetation management. Of course, on the West Coast is a big deal. So we think there's a lot of opportunities for machine learning in these areas. So with that, again, if you have any questions, feel free to ask them at the end. Back to you, Jana.
Great, thanks, Terry. It's always more interesting to hear about all the benefits and lessons learned from real customer experiences. It was very informative to learn about the benefits of maintaining a single source of networks and subnetworks within Esri's utility network, and how to potentially lower the cost of converting paper substation drawings through machine learning. Once again, I want to say thank you to Larry, Terry, Remy, and Ray for all of this great information. Now, before we get to your questions, I want to share just a few thoughts and recommendations for moving forward. My main recommendation is to at least get started down the road ensuring your GIS, which is a source for the connected model, has accurate and complete data to support progressive applications like an advanced distribution management system. Hopefully the information that the team shared today will help you begin planning for distribution grid modernization. Getting off the dime can be hard because let's face it, it's human nature to be worried about change. We talk with organizations every week who want to get started but have encountered roadblocks from system stakeholders who are resisting the changes. I found that the best approach is often to take some small baby steps. For example, a small proof of concept can help build confidence and gain internal support before you start taking bigger steps. If you haven't already, my next slide outlines a couple of approaches that you could consider. These have worked really well for our clients, so I wanted to pass them on. If your organization is pretty nimble and allows small proof of concept projects, option 1 might be a good one for you. It's pretty simple. We hold a discovery workshop to confirm EMS and ADMS modeling within the substations and validate requirements and demarcation points from transmission through substation to individual feeders. This workshop will focus on the data required to drive the advanced applications that a customer intends to deploy. Option 2 is used for utilities that prefer a bit more planning up front. We create strategic roadmaps to give your utility the big picture so they can move forward with confidence. The strategic plan provides an overall game plan that prioritizes the required tasks so that you can get the best bang for your buck as you move forward with grid modernization in a phased manner. I found that these are super effective if you need to secure executive support. We know what it takes to go from start to finish on these projects. Plus, we're an engineering company at our core, so we really understand the intricacies and nuances of the utility business. If you're interested in having Power help you get started with any of these items, I've included Larry's contact information on the next page. He would really love to talk with you whenever you're ready to start moving forward. All right, so we have a few minutes left. I'd like to look at some of the questions that we've received. If we run out of time before we can answer all your questions, we will include written responses when we post the recording of this webinar. Okay, so let's go for it. The first question that I see is, how do you propose to get data into these systems from a mixed environment of both the Esri geometric network and the utility network? All right, so we talked about those separately, but a mixed environment is a possibility during a phased implementation. Larry, this sounds like a good one for you. Do you want to chime in on this one?
Sure. So I'm assuming you're talking about the substations maybe being in the utility network and your distribution is still in the geometric network. Good question, totally possible. So just like we utilize the stitching point to traverse the network at Portland, we would do something similar by utilizing traditional methods to extract the geometric network, and then we'll utilize Esri's JSON geoprocessing tool to extract the utility network. The benefit of our group is that we are familiar with the middle tables that the planning or ADMS systems use. For example, common information models, multi-speak, proprietary intermediate data files, things like that are placed into like an XML file, these middle tables usually, and then they're consumed by these operational systems. So we can put together in this XML file, we put together your substations in one section of it, and then we'll use the traditional methods to put the distribution pieces into that XML file. Yeah, but not a problem.
Cool, thanks, Larry. All right, so here's another good one. How long does it take to train the machine? And how long does it take to then run the model against an image? Terry, do you wanna take that one?
Yeah. Our project, we took 100 images and sampled them. We took them and manually labeled them. So it took about 25 hours to go through all 100 images to create that training set. So about 15 minutes per substation drawing, if you will, to label it for the training set. Then once you have the training set, it takes about 5 or 6 hours for the model to be built. And this is highly dependent on your resources. You know, we ran it on a machine with very limited GPU, and it took days. And on a machine with 32 gigabyte of GPU, it took 5 hours to build the model that then we could then run against all the other substation drawings. And then it took about 2.5 minutes to extract those detected features, put them in the GIS, and to do all the processing to create the line work. It was about 2.5 minutes per substation. You can see it's pretty quick once you get the model trained. Imagine if you have 500, 600, 700, 800 substations, it could be a substantial savings, especially if you're trying to get them into a geometric network, which it'll create. Hope that answers the question.
Yeah, that's great, Terry. Thanks. All right, here's a good one too. Why is going to the UN going to improve your integration with Windmill? I have Windmill and Dispatch. So Larry, do you want to take that one?
Sure. So in Chelan's case, you know, I know you have Windmill as the planning, just to let everybody know, and Dispatch is the OMS portion of that. But in Chelan's case, the MillSoft standard extract tools aren't currently ready for the UN. They don't have that extractor for the UN, or at least they told me at the Distributech last year that they weren't going to be ready for that for a couple years. So we talked with MillSoft at Distributech, and we went through some of the tricky methods, like for multi-upstream sources and the STD formats, as well as the SEQ formats. And we came up with daily extracts for Chelan to support that ADMS, which would be similar to your Dispatch OMS. So if you can get direct daily extracts from your UN via MillSoft's, I don't know that they have an extract method yet. And we utilize that JSON format, and it's a tool that it's an Esri geoprocessing tool. So we do have that extractor ready for.
This is Ray. I can help answer that question too.
Go ahead, Ray.
Our GN to MillSoft extractor never worked very well. Our planning engineer had to make a lot of corrections, so we only run the models once a year. Last year, he just spent hundreds of hours correcting all the errors, because the GN actually allows some imperfect topology when you try to export it to another system. Well, now by running the GN to UN migration, that fixes a lot of these data and anomalies that MillSoft couldn't handle. So the extract now from the UN, directly from the UN to MillSoft, has cleared up a lot of the errors. In fact, most of them. Our planning engineers, he's a happy as can be right now.
Great, thanks, Ray.
Great, thanks, guys. Appreciate that. So I know we're at the 45-minute mark. Maybe this is just a real quick question that we can end this with. So how much lead time do we need to be able to implement the UN prior to a DMS or ADMS? Larry, let me send that one to you as well.
Yeah, there are multiple dependencies with that question. Selection of what ADMS you're going to use, how advanced you will get with the apps involved, like volt bar optimization or fault location, the size of your service area, how detailed you want to get in your new UN model will also play a part. I would just say give us a call and we'll help you sort it out, or get you some budgetary estimates and see what kind of track we can put you on, like that slide that Jana showed before. maybe you need just some roadmap type of thing at first.
Excellent. Appreciate that, Larry. All right, everyone. Well, I just want to close by saying thank you to everyone for their time and attention. Be safe and be well.